So while we're waiting, I'll talk about a blog post that I recently made. A recent article came out about why cheap and deep learning is so successful. And it's an interesting article, which not a lot of meat to it. It mostly discusses some analogies between deep learning and renormalization group theory, theoretical physics, and chemistry. However, the article does have an interesting point in the appendix where they note the difference between analyzing a partition function, which is what we see all the time in something like a restricted Boltzmann machine, and computing probability distributions, which we are typically trying to do in certain types of machine learning algorithms. And so the blog post I wrote essentially takes the appendix from the paper and looks at it within the context of restricted Boltzmann machines and the partition functions and free energies that come out of restricted Boltzmann machines, and goes through and I derive, really work through the proof in the appendix of the paper using restricted Boltzmann machines, and then demonstrate how the idea of renormalization group theory, the renormalization group constraint, actually looks like a type of layer normalization. And so I invite you to read it. We just posted it this weekend, and hopefully it will be insightful to you. Okay, while we're waiting, we're going to try and do the invite again. We're trying to get Roshan Fernando on the air. Hasn't come on yet. While I'm waiting for Roshan to come online, I'll also mention a new project we've started, which is to extend restricted Boltzmann machines using the tap equations from theoretical physics. The tap equations are a formulation of statistical physics which lets us solve for the solutions of spin glasses in the high temperature limit. It's an old technique which was developed in almost 40 years ago, and it was sort of the original methods. The tap equations were the original method used to analyze the convexity of the energy landscape of spin glasses. And it was shown that way back when that spin glasses have an exponential number of saddle points above a certain threshold, and that all the local minima are thought to be concentrated near the bottom. This, of course, is a new result that's come out of Lee Kuhn's group at Facebook, but this has been known in theoretical physics, at least suspected for a long period of time, at least in the high temperature limits. In low order tap equation, not an exact solution, but a good hint at sort of where to look. And of course, it's now been verified. So the new methods are something that Hinton talked about many years ago, but wasn't able to develop, and now we seem to have got working, is the ability to use the tap equations to solve as an alternative solver for restricted Boltzmann machines. So instead of using contrastive divergence or persistent contrastive divergence, one can use this thing called extended mean field theory, which implements second order or third order tap theory in order to write down a solver for an RBM. And the difference is that typically in an RBM, it looks like when we evaluate the free energies, we're doing Gibbs sampling. But Gibbs sampling can be done in the mean field approximation. The tap equations let you go beyond the mean field approximation to have second order corrections, Onsager corrections, mini body corrections, maybe even renormalization corrections. And so the solutions of the restricted Boltzmann machine, at least on every update step, instead of looking like one or a few steps of Gibbs sampling, looks now like a few iterations of trying to solve a fixed point equation. And because you're solving a nonlinear fixed point equation, you actually can go beyond the mean field theory. And so the claim is that this does a little bit better. It's always hard with to make these methods really accurate, but it's a nice extension. And one of the projects we have going on is to get it into scikit-learn. So we'd like to modify the Bernoulli RBM in scikit-learn. Okay, we're going to try to send the live stream invite again. We'll try one more time. So we've sent the live stream invite. I don't know. Are you not getting this? So let's just stand by. So as I was saying, the goal is to modify the Bernoulli restricted Boltzmann machine, Bernoulli RBM class within scikit-learn, and extend that to have the EMF solver. And so we started a small project to do this just as a hobby project to kind of see whether we can make a little bit of progress with these old methods and, get some connection between statistical physics and machine learning. So anyone interested in, join in, we're happy to have contributors. It's an open source project. The goal is to make a pull request and, to on scikit-learn so and get it accepted. So that's what we're trying to do. I'm going to try to send the invite one more time. Okay, I'm going to try a different email. Okay, so we're trying one more time to connect to our questionnaires. If they don't connect this time, anyway, back to tap equations. The idea was actually developed. The idea is that when you're looking at the free energy of a restricted Boltzmann machine, you're trying to solve a restricted Boltzmann machine on every update step of the gradient. You're trying to evaluate the free energy, and it's difficult to do. And the methods like contrastive divergence and persistent contrastive divergence are really estimating the free energy, and they don't really say it this way, I guess, because people in the machine learning community aren't accustomed to working with free energies and renormalization, so they recast all the language, but it's fairly, in statistical physics, it's fairly straightforward to see what's going on. And the tap theory allows us to get very, very high order approximations to the free energy, so it allows us to get in a very, very complex nonlinear corrections which go beyond the simple mean field correction. So it's a very nice, fairly straightforward once you work through some of the mathematics, and if you've done a little statistical field theory, you'll see immediately what's going on. If you haven't, then you'll learn something about field theory. Okay. So this. Okay, I don't think this is going to work, so we're going to try again. So this is our first live broadcast. We'll try and do this again, maybe later today or next weekend, and sort of a new idea of trying to have deep learning Q&A. So hope to see you then. Have a great weekend.